Welcome viewers. In today's lecture, we are at the first segment of ADC. An ADC is a system that converts an analog signal to its digital equivalent. ADCs are used in computers that converts an analog input to its equivalent binary format. ADCs are also used to convert an analog video to its equivalent digital format. In an ADC, the input analog voltage can have any range of values, but the digital output can have only 2 to the power n discrete values for any n-bit ADC. The whole range of analog voltage is represented using a 2 to the power n intervals. This is known as quantization. Each interval is then assigned to an n-bit binary code, which is known as encoding. Considering an analog voltage in the range 0 to V and a 3-bit digital output of any voltage in this range. This is then divided into 8 intervals of the size S is equal to V by 8, where each value is assigned a 3-bit value. Hence, we see the whole range of voltage in an interval is represented by a digital value. This leads to an error known as quantization error. Here, in this case, the maximum quantization error for any analog voltage Vx in the given range is V by 8. If we choose the middle 6 intervals, that is S is equal to V by 7, and the top and bottom intervals are of size S by 2 is equal to V by 14, then we can reduce the quantization error of an ADC. This shows that the maximum quantization error will be S by 2 is equal to V by 14 for any analog voltage VA in the range 0 to V. The quantization error can also be denoted using LSB. In this case, the maximum quantization error is plus minus half LSB. Parallel flash AD converter. A 3-bit comparator ADC is shown. VA is the analog voltage that needs to convert it to the digital voltage. The full scale of voltage is represented using V, each divided into reference voltages VR1, VR2, VR3 and so on are generated using resistor network. The voltage VA is compared simultaneously with reference voltage using comparators. A 7-bit output is obtained from the comparators and stored in the latches. This 7-bit signal is converted to a 3-bit signal output by using decoder circuit. The principle of ADC is the simplest and fastest. Its main disadvantage is in rapid increase in number of comparators with the number of bits 2 to the power n minus 1. Successive approximation of ADC. The comparator serves as a function, a balance scale. The output of the comparator is used for setting or resetting the bits at the output of the programmer. This output is then converted to equivalent analog voltage from which the offset voltage is subtracted and then applied at the inverting input terminal of the comparator. The outputs of the programmer will change only when a clock pulse is applied. The programmer initially sets the MSB to 1 and rest bits are 0. This is converted to analog signal using DAC and the comparator compares it with the analog input voltage. Here, if VA is greater or equal to VI, the output voltage Vout of the comparator is high and sets the next bit. If VA is less than equal to VI, the output voltage Vout of the comparator is high and sets the next bit and resets the MSB. For an n-bit converter, the number of clock pulses required will be n and it is hence slower than parallel comparator AD converter. Counting ADC. The successive approximation of ADC can be converted to a counting ADC. This can be done by replacing the programmer with an up counter with a clear input which must be clocked. The output voltage of a DAC is compared with the analog input voltage. If VA is greater than equal to VI, Vout is equal to 1. If VA is less than equal to VI, Vout is equal to 0. For as long the analog input voltage VA is greater than VI, the comparator output is high and clock pulses are transmitted to the counter. Now when VI exceeds VA, the comparator output VO changes to low, disabling the AND gate and the counter stops counting. The maximum clock pulses applied for conversion is 2 to the power n for n-bit comparator. In today's lecture, we have learned Introduction to ADC, Quantization and Encoding, Parallel Flash AD Converter, Successive Approximation of ADC, Counting ADC. With that, we are at the end of this lecture. We will meet again in the next lecture. Till then, thank you and goodbye.